For my project, I created an ARM processor and an FPGA that is compatible with many of the ARM instructions. I based it off of the M0 spec, which uses ARM version 6. I called it the Evenstar ARM M0 compatible processor, based on a name that I've used in the past, Evenstar Systems. In creating the processor, I used the Digilent Basis 3 board, which includes a Xilinx Arctic 7 FPGA along with onboard I/O and buses to allow attachments to other I/O. I developed it in Verilog using Xilinx Vivado. I also used some features of System Verilog. The demonstration I'm about to give shows a couple programs that I wrote, including a calculator program. When I demo my project, what I'm showing is an operation of two programs that I wrote, but that was only a small part of my project. I wrote the project in ARM machine code. I wrote this code in ARM machine code. The main part of my project is the processor that I designed to actually execute the machine code instructions. So first of all, I'm going to just show a short program that I wrote just to show the operation of the onboard I/O. I have right now I have basically it tied so these switches show up as values on the 7-segment displays. You can see there's a 8 in hex. You have an 8, 6, or 7 here. I can change it to a 6 there by flipping a switch, or then 6 and 3. I can change to 2, and so basically it's tied to the switches. They're not directly tied to the switches. It's actually machine code that is taking the values from one location and writing them out to the 7-segment displays. I also have it so I can push the buttons and they show up as repeating patterns on the LEDs, and I can push multiple ones and they'll repeat. And I have one rogue LED. I'm not sure why, but anyways, that's the first program. So for my second program, this one's actually was a lot bigger program. It's a calculator program that I wrote, and I can actually go through and enter values. And this was pretty involved writing this in machine code. But the if I can go ahead and enter a value like say 7 plus 16, which is, and hit enter, and of course the answer is 17. Well, actually, when you type the values in decimal, the result actually shows up in hexadecimal, and I wasn't trying to do that to be clever or anything, or to add some strange feature. I just did that because it would have been really hard in machine code to program a way to convert the number to BCD before I showed it in ASCII on the display. Especially when my processor that I created doesn't actually have divide or modulus instructions. So just a few other things I can do. Say 25 times 8, and that is C8, which is actually in decimal value of 200, just like it should be. I can also say 10 minus 5 gives me a value of 5, which coincidentally is also 5 in decimal. If one thing also, I can say 10 minus 11, and that gives FFFFFFF, which is the 2's complement 32-bit representation of -1. So it's doing exactly like it should there. I had extra buttons on this keypad, so I went ahead and did. I can do this also. I can say 119 and say and. I think this was and. Yeah, that's and 158, and that does a bitwise and of the value, and that comes across as 16. And the and I also can do a say 30583, or it's bitwise or with 34 952. And that comes out as FFFF, which is just because those numbers in hexadecimal that I just entered are actually 7777 and 8888. So it works out pretty well. Anyways, that is my project, and that's basically as much as you can see it operating from the outside. There's a lot of again, the biggest part was actually creating the processor that's running those instructions. Thank you. I was able to get many of the instructions to work, including most of the data processing instructions other than PSR transfers. The multiply and multiply with accumulate worked great. The single data transfer, I was able to get those to work. Also the branch instruction and branch with link instruction. The only ones that I really have left are, of course, PSR transfers, the single data swap, block data transfers, coprocessor instructions, and software interrupts. This screen shows a high-level overview of the project generated by Xilinx Vivado. The inputs are shown on the left and the outputs on the right. The CPU module is the heart of the project. One thing I'd like to note is that the only outside connections that it has are to the clock or reset, which is labeled button C, and to the bus. All I/O goes through the bus module. I created input and output ports to the bus, which I then tied to memory. The CPU must then access the I/O via memory load and store instructions. Some of the I/O, specifically the buttons, switches, and LEDs, are tied directly to pins that can be easily accessed. I tied these directly to the bus module's I/O ports. For the keyboard, 7-segment display, and the ASCII display, I created drivers to simplify the instructions needed to manage them. The keyboard and display module were actually based off of modules that were written by Randall Jack, though I made some extensive modifications to them, especially to set up handshaking. The rest I actually wrote from scratch. I called my top-level module the CPU interface. It connects the physical I/O pins to the bus module, which is in turn connected to the CPU module. It also distributes the clock and the reset pins. The CPU is based on the document ARM Processor Architecture by Jin-Fu Lee. Examination will show most of my modules match the diagram from the document. I also extensively use the ARM 7500 FE datasheet for the instruction set architecture and to write the machine code. The system bus is based on the ARM manuals for the M0 core and also the AMBA Lite bus manuals. Memory is based on templates described by Xilinx Vivado manuals, so it took a huge amount of research. I broke the memory up into groups, which I called segments based on old x86 terminology. I used the high 16 bits of addresses for the segment address and the low 16 bits as offset addresses within the segment. In most cases, I actually discard the low 2 bits because everything is 32-bit aligned, though in some cases when I need to do byte-sized transfers, I use those low 2 bits. My machine code is contained in the ROM module. I created a RAM module which uses block RAM. I also have device input and output modules which use distributed RAM, and those are the shared memory that tie the I/O ports to memory addressable by the CPU. Now I will quickly go over the required goals and stretch goals for the project. First, I wanted the processor signals to match the M0 and ARM version 6 specifications. I said the signals would be present even if they were not used. This diagram shows the CPU pins. It was generated by Vivado based on my actual design. Some of the inputs it shows tied to ground because in Verilog I forced those to logical low levels. One of my requirements that I set up was actually based on some issues that I'd had when I worked on this for a few weeks before class. There were some timing issues, problems with getting data at the right places at the right time, and I was using just straight always statements everywhere. And I decided that I would fix that by using the system Verilog format of always statements. In other words, always FF for flip-flops and always COM for combinational logic, and always latch wherever that seemed appropriate. This actually did end up helping a lot. It identified some issues that I was having. Um, and with Always Latch, with that one, there was only one spot where I ended up trying to use that because I wanted to hold a value, but I didn't want it to take up a clock cycle. It ended up not working very well, and so I ended up finding a better way to do it, and so I ended up not using Always Latch at all. There were a few cases where I did use Always, mostly in the drivers that I got from Brother Jack. Um, Also, in my reg file, I used an always statement because it was complex enough that I wasn't sure how well it would work with a flip-flop always FF statement. Another requirement that I had was to create a modular memory system. I already described this in previously, so I won't say a whole lot about it. I mostly wanted to break my memory up basically into segments, and I ended up, after doing a lot of research, following fairly closely in a lot of ways the AMBA Lite protocol. The other requirements I set were to do variable size memory transfers and to follow the ARM version 6 fetch, decode, execute pipeline. As a note regarding the pipeline, memory transfers require an extra state. In my example, here we see a store instruction, which is working its way through the pipeline. Part of the fetch is not shown where the value comes from memory. It is put into the read register on a half cycle. To fix a lot of issues that I was having, I decided to have transfers happen during a half cycle in 2 cases and only 2 cases. And one is where I load the address register, and the other is where I load the read register. That fixed a lot of issues. So here we see half of the fetch stage when the instruction goes into the read register. During the decode stage, the instruction goes into decode hold and the decode registers. Decode hold is an extra register that I set up for delays that can occur when we have an extra cycle happen from load and store instructions. Combinational logic, also during the same stage, combinational logic takes the instruction and breaks it into operands and signals, and that's that decode signals value that's shown. In the execute stage, I take those signals and I pass them on to other flip-flops. In this example, execute shown as taking 2 cycles, though the memory actually goes into RAM halfway through. For store instructions, I'm storing that value after the first cycle, but I'm using that other cycle to change the address. I'm not sure if that matches spec or not, but it's how I was able to get it to work. The red dot, that shows where the data actually goes into RAM. It goes from the R0 register into RAM. Regarding variable size memory transfers, version 6 of ARM only allows 2 sizes of transfers, and that's 8 bits or 32 bits. Other versions allow more sizes. In this first example, for this first instruction, we're doing a 32-bit transfer and the value is 04060000. Second instruction is a load instruction for a byte-sized value, and you can see where the red dot is that the value that's loaded is actually the second byte of the from RAM, which is at location 202. This is the value 0B, and it goes into the low part of the register. That's what the specification actually requires. You can also see that decode hold in this case was used because we had just done a store instruction. The next instruction simply modifies the value in R0 by doing an OR instruction so that it becomes 7B. And the next instruction is simply a byte-sized store. It takes the low part of register R0 and puts it back into RAM, but in a different location. The next requirement was to tie to tie the onboard inputs and outputs, specifically the switches, buttons, LEDs, and the 7-segment displays, to tie those to shared memory so that they could be basically accessed by the CPU via instructions. And I demonstrated that already in the first program that I showed. So the next requirement was to do unconditional and conditional jumps, which ARM actually calls branch instructions. One thing with ARM processors, all instructions start with a condition code. The majority you see that start with E, and that means to always execute the instruction. Here we see examples of some that start with 0, and that means to only execute if the Z flag is set. In the top example, there's an EA instruction. That is a jump instruction that always is executed, and you can see how expensive it is because it clears out the pipeline. All the values go to 0 in the pipeline, and then it has to refill the pipeline up again. In the example on the bottom left, there's a 0A instruction that's one that only executes if the Z flag is set. In this case, by the time it gets towards executing that instruction, the Z flag is not set. That's the bottom value. So the branch doesn't occur. But in the next example, we see that same exact instruction where the Z flag is set, so the branch does occur, and again you see the pipeline get cleared out. The final goal that I said is required was to implement all of the unconditional ALU instructions, and by this what I meant was the data processing instructions as well as multiply. And this was actually the easiest part of the whole project. I already showed most of the functionality when I demonstrated the calculator program. One of my stretch goals that I set was to be able to execute other conditional instructions. For some reason, I thought this was going to be a lot bigger deal than it was. I had already set it up for branch instructions, and that did take a fair amount of time because I had to set up the flags and how to set the values of those flags, and also be able to block execution based on the state of those flags. But by the time I did it for the branch instructions, I was pretty much done. With conditional instructions that aren't branch instructions, they're actually pretty cool because if they get executed, they don't flush out the pipeline. So that's a pretty nice thing about them. Two additional stretch goals I had were to use the ASCII display and the keyboard input that you can get from Digilent. These can actually plug directly into the Basis 3 board. There's some work that has to be done to get them to operate correctly. I saved time on this by using some modules that I got from Randall Jack, and I basically added some handshaking in and tied them into my system, and I was able to show that these operate in my calculator demonstration. Another stretch goal that I had was to create a practical machine code application. Knowing about the ASCII display and the keypad, I had a calculator program in mind all along, and these excerpts that I have right here are actually part of the calculator program that I wrote. That took about 200 lines of code to set that up, and took quite a bit of time to write it out in machine code, but it works pretty well. I also had another stretch goal to create a separate increment module. Before I started out doing this as just another part of my register file, but I believe this more closely matches some of the models that I saw. It takes the address register value and basically just increments that value by 4, and it modifies both the address register and the program counter, which is R15 in the register file. I had to do a little bit of work to set up a way to override the value, the address value in different cases, but it wasn't too bad. My final stretch goal that I completed was to use onboard RAM. At first, I actually misunderstood this when I read that there was RAM on the Basis 3. I thought that it was actually RAM built into the Basis 3 board, but after further study, I realized that there is actual RAM inside of the Arctic 7 FPGA chip, and it's called block RAM. And after more study, I was able to figure out from Xilinx how to use that RAM, how to properly set it up to be used. And you can see the little tiny bit of it that I'm using on the FPGA, and also down below it shows it in the run statistics for the synthesis process and for the implementation. I had another goal where I wanted to use an external ROM chip to store my machine code program, but I never was able to have the time to finish that goal. I had a number of other goals that I would have liked to have completed. Um, One was that I had some buses that I wanted, especially one bus that bothered me that I had added in to help things out, but I don't know that it really belongs in there, and I think it could be done away with, but I ended up just leaving it in for sake of time. I also really wanted to package the processor as an IP module. Um, there were a few other ones. Other ones I didn't think I would get to anyways. The custom V6 multiplier, there's actually a specified way to do the multiplication. I ended up just using Vivato's built-in multiplier. The I originally wanted to set up divide instructions, but I don't even know if there are any in the specification that I have, or it just has to be done through software. The fault handling, I figured I wouldn't be able to get to that, and interrupt handling, but eventually someday I would like to add those in. So overall, this has been a wonderful project. I have learned so much and just ran into all kinds of issues along the way. Really spent just hours and hours working through timing diagrams and sometimes just reading through manual after manual and post after post and just trying to figure out how to get everything to come together, and I'm really pleased that in the end I was able to finish all my regular goals, and I was able to complete my most important stretch goals that I had, and I'm glad for this experience I had to learn.